Today there is a important focus from the type of frequency domain filters. So in this examples, in this study of the second unit, say that the type of frequency domain and then image transformation, fast Fourier transformation, discrete cosine transform, and the Karhunen-Loeve transforms. So first of all, study about this basic image transformations. Before that, study from the type of frequency domain. So in this concepts, I think force with the type of the spatial domain. What is the major work of frequency? The number of times that a periodic function that repeats the same sequence of values during a unit variation of the independent variable is called a frequency. In this type, you will come to so many transformation techniques are there, like that translation, scaling, rotation. In this major work of this Fourier transform of image processing, in this sampling, what is the major process with step by step derived, and 1 and 2 dimensional discrete Fourier transformation, and what is the major role for convolutions of this Fourier transformation. Like that, will become to improvement of this type of frequency concept. In this frequency transformation, before that is say this the type of this Fourier series and transformation. This French mathematician Jean-Baptiste Joseph Fourier was born in the year 1768 in the town of Actuary, about this midway between this Paris and Dijon. In these cases, you come to the here to develop in this year of Fourier transformation of what is a periodic or non-periodic functionality, and continuation about this in this domain. Fourier domain, you will say this frequency domain. In cases of this frequency, fast Fourier transformation algorithm in the year 1960 onwards will be revolutionary of this field of signal processing. So this is this the way of periodic function. Among this that in year 18707, that is here come to this periodic function could be represented as a weighted sum of this sine and cosines. So met with skepticism, we come to say that the fast Fourier transformation to applicable with the what is the computational advantages of this m by m, respectively come to this image both m and n equal to m equal to n. So in this is a non-separable kernel of to be defined from kernel location. Center Cn of m equal to m square, capital M square, small m square divided by 2 m square log to m square. It will be representation, the simplification about this m square divided by 4 log to m. So in these approaches of computational advantages among this type of kernel fast Fourier transformations, the m value with respect to the type of dimensionality. And small m represents the type of the intensity values. So in this concept, we'll come to study about this complex number, what is the Fourier series, and that 1D, 2D. So mainly consideration among this Fourier transformation. In our syllabus, only it focus with image transformation along with fast Fourier transformations. So here this is sampling of this fast Fourier normal functions of 2D. This is Fourier transformation DFT. Fourier transformation normally to force with the type of maximum of positive and negative of value. So it will come to analyzing from the different type of functions. I will force with only for fast Fourier transformation. So here DFT means you'll come to say the type of this information along with the Fourier transformation. So two dimensionality. So here relationship between the sampling and the frequency intervals. So discrete Fourier transformations is especially used from most of the cases from the frequency domain only. So here 2D impulse and shifting property, 2D variables, 2D continuous of a Fourier transformation pair. So how to this project with a mesh function in MATLAB, 2D impulse train. So here this is everything from two-dimensional concept. So 2D is a 1D extension of 1D concept. So nature of here this theorem will come to along with the type of any type of images with illustrated the resampling of natural image as aliasing and more patterns. So here this is a pattern of dot per inch that we come to analysis from fast Fourier transformations. 2D discrete Fourier transformations. I think the inverse of IDFT. Relationship between the spatial and frequency, the translation and rotation concept. Here the periodicity, symmetry property, spatial domain and the frequency domain. Fourier spectrum and the phase angle. So most of the cases will come to the frequency low pass and high pass filtering, especially if they come to analysis from the 1D, 2D fast Fourier transformation. So in this image processing, the normally to force with the type of this image from original, and then it will be changed over from this frequency level, and then the resultant of the value come under this effect of this frequency level. So here there's a lot of DFT definitions and then concept, spectrum, phase angle, polar representation, power spectrum, average value, and convolution correlation and separability, and the inverse of DFT and linearity, rectangle sine, cosine, and a cosine. So here this additional characteristics of frequency domain will come to analysis from the type of this microscopic SIM, the Fourier spectrums of to be analyzed from material sciences of physics, frequency domain filtering fundamentals. Now we'll move to this another interesting topic from the Fourier transformation is the fast Fourier transformation. 1D, 2D, and IDFT, the inverse of discrete Fourier transformations. So especially come to this changeover from the type of pre-processing step of filtering denoising steps, spatial and frequency domains. So what are the major advantages of frequency domain this Fourier spectrum? So image smoothing and using low pass frequency domain filters and ideal low pass filters, and then I will come to analysis from the type of high pass sharpening and high pass filters, Gaussian low pass filter, Butterworth low pass filter, another additional example for low pass the ideal Gaussian and Butterworth. So another resolution among this type of resulting of value, and another one for image sharpening using high pass filter, the same ideal Cosine and Butterworth these filters. So why to say the type of this image processing before that they come to analyzation from image transformation. The pre-processing step is very, very important. This is a Laplacian of frequency domain. Here this is unsharp masking and high boost filtering, and then high frequency emphasis of filtering techniques. So homomorphic filtering. So all the filtering techniques to be supported from frequency domain only. Poisson emission tomography vector, and selectively and a band reject and a band pass filters. So not filter. So all the type of periodic functions to be supported from, that is help of this DFT and IDFT. So in this concept, this is our syllabus. If we come to for correct, this is the type of the fast Fourier transformation. We have focused attention thus for this theoretical concept and an example of filtering in this frequency domain. So here we say important development of basic understanding of methods by which Fourier transformation to computation to can be simplified and speed up. So this is the main issues. Separability of this 2D DFT, two-dimensional discrete Fourier transformation into 1D transformation. So we can write this equation f of u comma v equal to sigma x equal to 0 to m minus 1 e power minus j 2 pi ux divided by m. Again another sigma function y equal to 0 to n minus 1 f of x comma y e power minus j 2 pi and vy divided by n. To combine with this both one, we come to say this the type of this value sigma x equal to 0 to m minus 1 f of x comma u v e power minus j 2 pi ux divided by m, where another f of x comma v means will be representation from the n value. So it is n value. So automatically you will come to say this 1D transformation will come to along with the type of 2D Fourier transformation. So computing this same idea to be invoked with inverse discrete Fourier transformation using a DFT algorithm. In this fast Fourier transformation works in this frequency domain would not be practical if we had to implement this equation directly, and another one will come to brute force implementation. Brute force algorithm implementation of this equation requires of this order of m n power 2. That means multiplication of both m and n whole square. So for images of moderate size is 2048 into 2048 pixel means in order to 17 trillion multiplications addition for just one 2D DFT. Excluding this is exponential, which could be computed once this is look up this table, the discover of this fast Fourier transformation. So the in this material, what is this order of in this computational work mn log to mn. So multiplication and addition to be saved to say this material presentation in this chapter. The practical value of this FFT to impressive needed. So the computation for 2D FFT will come to 2048 into 2048 images. Will come to this order of 92 million multiplication and addition. So although that is FFT is a topic covered extensively in a literature on signal processing. So in the successive doubling method, the original algorithm that led to birth of this entire industry. In this 2D DFT can be implemented by the successive process of the 1D transformation. So we need to focus only on the FFT of one variable. So in derivation of f of t, it is customary to express for this equation 4.44 in the form f of u equal to sigma x equal to 0 to m minus 1 f of x, w of ux of m. So in this respectively m equal to 2 power p, m equal to 2k. So in this equation we come to substitution from the type of this value. Finally, both f even and f odd will come to representation from the type of fast Fourier transformation. So in this final, both f of u plus k equal to f even of u minus f odd of u, w to u to k. So in this equation to be representation from the type of transformation, and both will come to analyzation from f odd and f even. So in this multiplication, to implement of this the value of m of p and a of p, that is from both the addition and multiplication value. So m of p equal to 1 by 2 m log 2 m, and then addition of a of n equal to m log 2 m. Finally, the computational advantages of this value of 1d dft to of f of t, c of m equal to log m divided by log 2 m. So finally, it will be substitution from this m value to 2 power p, c of p equal to 2 power p divided by p. So in this value will come to this kernel to be analyzation from c of p equal to 2 power p divided by p. In these cases, fast Fourier program also is readily to available principally over from this application. So next is cases, you will come to this analyzation from in your syllabus, image transformations along with f of t and discrete cosine transform. In this transformation techniques, forced with the type of image processing work directly to move to DCT, the cosine transformation technique. So in this DCT, major role from your work to compare with DFT. So what is this major role from cosine transformation? So for example, the n by n cosine transform matrix C in the set of C of k n is also called a discrete cosine transform DCT. In this C of k n to be representation along with 1 by 2 square root of n, is given that k equal to 0, that interval of n value is 0 less than or equal to n and less than or equal to n minus 1. Otherwise, square root of 2 by n of cos by of 2 n plus 1 of k divided by 2 n. If the k is of interval 1 less than or equal to k less than or equal to n minus 1, or 0 less than or equal to n and less than or equal to n minus 1. In this case, that one-dimensional DCT is a sequence is a representation of u of n. So in this v of k and alpha k, that is value to be representation from the type of this one-dimensional DCT. So image transformation along with chapter here, the cosine transform of this image scan line shown in this figure 5.4. So k is the traveling of this line of intensity value 1 to 2t5, and then y power k is cosine transformation techniques. Carry on. So the inverse transform is like that u of n. So it will be representation from the type of cos theta and then alpha value. So the basic vectors is 8 by 8 of DCT. In this performance of the two-dimensional cosine transformation, substitution from a equal to a power star, a star equal to c. So in this property of a cosine transformation like that, here this are two important property. The cosine transformation real and orthogonal, that is called c equal to c star. So implies from c power minus 1 equal to c of c power t, the cosine transformation technique. The cosine transformation is not the real part of the unitary DFT. This can be seen by inspection of C and the DFT matrix F. However, the cosine transform of a sequence is related to the DFT of its symmetric extensions. So here this is cosine transform examples of monochrome images. Here this is a cosine transform example for binary images. The cosine transformation, the vector n elements can be calculated in this order of n log to n. Operations via n point f of t. So both will be recorded from even and odd elements u of a n as will come to denoted from this equation from 5.91. Each and every summations into even and odd terms uses to obtain that is a formula to be applied from this value. So inverse cosine transformation is also performing from the data points, both odd and even data points. So in this direct algorithm, especially there will be help of this inverse FFT, inverse DCT, and direct algorithm. You will come to application from the type of complex arithmetic. The cosine transform has excellent energy compaction for I correlated data. This is due to this following property. The basis vectors of the cosine transform, that is the rows of C, are the eigenvectors of the symmetric triagonal matrix of Q of C, defined as Q of C equal to 1 minus alpha 0, and the second is minus alpha and 1, and another value that is the value to be in place from 1 and minus alpha from this next level. So here this is say this is 0, so minus alpha to minus alpha and 1 to 1 and then 1 minus alpha. Finally, the representation proof of this left off and exercise. The sixth property is also the cosine transform is very close to Karhunen-Loeve transform of first order stationary Markov sequence of a length n, whose the covariance matrix is given by this correlation parameter P is close to 1. So the result will come to application from both transformation techniques. So this is the cosine transformation. So another will move to Karhunen transformation. So in this KL transformation, Karhunen-Loeve transformation, simply we say KL transform. So originally introduced from the series of expansion for continuous random process by Karhunen and Loeve. For random sequence of Waterling, the first studied what was called the method of principal component, which is the discrete equivalent of the KL series expansion. Consequently, the KL transformation is also called the Waterling transform or the method of principal component. For a real n by 1 random vector u, the basis vectors of the KL transformation is given by this orthonormalized eigenvectors of its autocorrelation matrix R. That is, R pi of k equal to lambda k and pi of k. It will come to representation from KL transformation. So many inverse transformation along with this kth column will come to representation from the type of pi of or star of t and then r of pi equal to that is the value of lambda equal to diagonal of lambda of k. So which is the representation from this KL transformation. So most of the image transformation considered earlier were functionally independent of the data. So the KL transformation to be depends on this statistics, what we mean by second order statistics of the data. For example, the KL transformation to be of a Markov 1 sequence, the covariance matrix of the zero mean Markov sequence of n element is given by this equation 2.68. It is eigenvalues of lambda k and then eigenvectors of pi of k are given by this lambda k equal to 1 minus p of p square divided by 1 minus 2p cos wk plus p square. So in this cases pi of k equal to m divided equal to pi of mk. equal to 2 divided by n plus lambda k power 1 by 2 sine of w of k m plus 1 minus n plus 1 divided by 2 plus k plus 1 by divided by 2. So normally that is the positive roots of the equation. Tan of nw, then we come to representation from the type of KL transformation. So this is major rule from to be applicable from the type of fast Fourier transformation, and then supported from DCT. Both will be quite nature similar because pi of k of m are a non-harmonic. A fast algorithm for the transformation does not exist. Also, KL transformation matrix is pi of t delta equal to of pi of k comma m. So this is this end of this second unit. Students already submit your assignment. Tomorrow is practical assignment submission and 17th or theoretical assignment submission. Thank you.